As someone who enjoys risk-taking behaviors, I would like to go skydiving someday. However, I'm sure I'm not the only one to wonder if there is a way to do it without a parachute. Well, on July 30th, 2016, a man named Luke Ikens officially became the first person to survive a skydive without the aid of a parachute or wingsuit. He jumped out of a plane, fell 25,000 feet, or 7,620 meters, and lived to tell about it. But how did he do it? Well, the answer lies in one simple word: physics. To be more specific, the veteran skydiver fell into a giant net that was suspended in the air by 4 cranes, one at each corner. That allowed him to minimize the impact that the fall had on his body, thus allowing him to survive. First, let's take a look at all the forces that Luke experienced at different times during his stunt. The moment before he impacted the net, the only 2 forces acting on him were the force of gravity in the downward direction, and the resistive forces due to air in the upward direction. At this point, he had been falling long enough that these forces were equal, meaning that he was falling at a constant, or terminal velocity, due to the net forces on his body equaling 0. At the moment he impacted the net, the upward elastic force due to the stretching of the net, combined with the upward resistive forces of air, exceeded that of the force of gravity, and he began to experience negative acceleration, meaning that he started slowing down. Finally, at the point at which his velocity becomes 0, the force due to air resistance becomes 0 as well, while the force of gravity and contact force due to the net are in equilibrium. This situation and how Luke was able to survive it can be examined conceptually by looking at Newton's second law, which states that the net force experienced by an object is directly proportional to the mass of the object, as well as the acceleration of the object. One of these variables had to be changed in the setup for the stunt in order for Luke to survive. The mass of Luke could not be decreased, so altering that variable was off the table. However, if acceleration could be decreased, then the force in Luke's body could also be decreased, reducing the likelihood that he would experience injury or death as a result of the stunt. Acceleration is directly proportional to the change in velocity experienced by an object, while it is inversely proportional to the duration of time over which that change occurs. Even if Luke spread out his body so as to increase the force of drag on his body due to the air, this would not significantly decrease his terminal velocity, and he had to come to rest at the end of the fall regardless. Taking both of these things into consideration, there was no way to meaningfully decrease Luke's change in velocity, so the only option was to increase the duration of time over which he experienced that change. As previously mentioned, this was accomplished by having him fall onto a huge net that greatly lengthened the time over which he was decelerated to a speed of 0 relative to what it would have been had he simply hit the ground. In order to examine Luke's stunt from a quantitative angle, I first looked at the forces present when he was at terminal velocity. It is important to mention first that it is irrelevant that he fell 7,620 meters, as it only takes about 450 meters for a human to reach terminal velocity. Nevertheless, assuming that Luke's total mass is 83.9 kilograms, the force acting on him due to gravity would be 822 newtons in the downward direction, meaning that the force of air resistance would be equal and opposite to this. To determine the net force that he experienced at the moment of impact, I examined the video of him falling and determined that it took him roughly 1.7 seconds to decelerate from terminal velocity of 53.6 meters per second to 0 meters per second. Dividing this change in velocity by this change in time gives an acceleration of negative 31.5 meters per second squared. Finally, multiplying this value by his mass gives a net force of negative 2,643 newtons. The math checks out, as according to the Occupational Safety and Health Administration, a person should not experience greater than about 8,000 newtons of force as a result of a fall, and this is much greater in magnitude than the force I calculated.